Hi there, Guilherme here, and welcome to GeeklyEDU Mathematics. Today we're talking about integrals. I know it's a very complicated topic for a lot of people out there, but today I'm going to teach you a very special way to transform some complicated integrals into easier ones to solve. So let's start. Okay, so let's start by the change of variables in the integral theorem, okay? So the theorem says this. So we have a certain function f that's continuous in a certain interval I, all right? And we have two numbers that are inside this interval I, two real numbers, okay? And we also have another function, g, all right? And the function of g in these two other limits, okay, c and d, that's also in this interval here, are continuous, okay, and g, the first derivative of g in this interval cd is also continuous, okay. So what we're trying to do here is this. We have a certain function of x, okay, the integral from a to b of this function of x, and we want to turn this function here, this integral, into another one based on this new function g, okay, which is continuous also, okay. So we have that the integral of a to b of fx equals the integral of cd from c to d of the function of g, okay, times the first derivative of g du. So it seems complicated, right? But graphically, it looks like this. We have a certain function of x, let's suppose this one, x to the third minus 1, and we're calculating the integral from 0 to 1. Okay, if you calculate this integral here, it will be negative 0.75. But see that the shape of this integral is not linear, right? So it's not that easy to calculate. So we want to transform this integral here into an equivalent integral, okay? For example, if we calculate this other integral here from this function, 3u over 2, you'll notice that 3u over 2 from negative 1 to 0, it's also negative 0.75. So we're basically transforming a certain integral into another one that's easier to solve. Okay, now enough theory, and let's go to practice, because that's how we really learn mathematics, okay? So we have this integral here from 0 to 1 of x minus 1 to the 10th dx. So, according to the theorem, we want to find a simpler version of this integral, okay? So let's call this x minus 1 of u, and then we have that x equals u plus 1. And, well, dx will be the derivative of u plus 1 du. Now if you calculate this derivative here, we have the derivative of a constant is 0, right? And the derivative of u du is 1. So we have that dx equals du. Good. Now let's take a look into the limits here, okay? So when x equals 0, we can go here, okay, x equals 0, u equals minus 1. And when x equals 1, these are our limits, okay, we have that u equals 0, okay, good. Now let's substitute our integral. We have that our integral here, so x minus 1 equals u, right, we defined this before, so we have u to the 10th, and dx equals du, so we have u to the 10th du. But now the intervals here change, okay? It goes from negative 1 to 0. And to calculate this integral here is pretty simple, right? So you just have u to the 10th, the integral of u to the 10th is u to the 11th over 11 from negative 1 to 0. And this is 1 over 11. Okay, now we go back to our first integral, and this integral is the same as this other one, and this other one is 1 over 11. So our first integral is equal 1 over 11. Now graphically it would look like this, okay? In red here we have our first integral, okay, x minus 1 to the 10th, from 0 to 1. So this value under the curve is the value of our integral. And now if we plot here the u to the 10th, okay, is this blue line over here, and you see that's pretty similar to our original one. But now we're calculating from -1 to 0. And notice that the area below these two lines here, from the blue line from -1 to 0, and from the red line from 0 to 1, they're exactly the same. So these integrals have the same value. Now let's calculate another example, right? We have this integral here of the square root of 2x minus 1 from 1/2 to 1. And let's transform this integral into a simpler one. So the trick here, we take 2x minus 1, okay, what's inside the square root, and call it u. So x is 1/2 of u plus half. And dx, we just derivate this times the u. So the derivation of 1/2 of u plus half the u is just half the u. So dx equals half the u. Now, let's take a look into the limits, all right? So for x equals 1/2, we have that u equals 0, okay? We can take a look at this right here, okay, in our first equation. So x equals half, this equals 1, minus 1 equals 0. And well, for x equals 1, we have 2 times 1 minus 1 equals 1. X equals 1, u equals 1. Now we go back to our integral. We have 2x minus 1 equals u, right? So we have the square root of u here. And dx equals half of the u. So we end up with the integral from 0 to 1 of the square root of u, half of the u. This 1 over 2 here is a constant, we can take it out of the integral, okay? And we end up with the integral from 0 to 1 of the square root of u. This is a very, very well-known integral, right? This is 2/3 of the square root of u to the third from 0 to 1. If we calculate it, it's equals 1/3. We go back now to our original equation, original integral, right? And it will also be 1/3. Graphically, it would look like this, okay? In orange here, we have our integral of the square root of u, half of the square root of u, okay? And in blue, we have the integral of the square root of 2x minus 1. Note that the equations are different. Graphically, they're also different, but the area below this red line from 0 to 1 is exactly the same area under this blue line from 1/2 to 1. Now here's a challenge for you guys. Try to solve these two other indefinite integrals, alright? Think about the theorem. Try to turn these equations into simpler equations, into simpler integrals, and write your answers in the comment sections. I hope you enjoyed the video and see you later.
More math videos are coming. Don't forget to subscribe and check out other topics.